Okay, to this point, if you're in my class and you're going through the lectures in order, we've talked about a lot of fluid statics. That is, things about fluids that occur when things aren't moving around, right? That's what static means, nothing's moving. So we've talked about pressure and density and the Archimedes principle and the buoyancy force. And to be certain, things like pressure and density are not exclusive to fluid statics. But when we start letting things move around, we will have to characterize them a little bit differently. So to do that, our first line of defense is what we saw in the last video, which is what's called the continuity equation. It's basically the flow rate equation. Q initial is equal to Q final, where Q is the flow rate. And what we decided is that this is A1, V1, where V is a velocity. Here's really a speed. We're not treating this as a vector, but it's not volume, is equal to A2, V2. This is the continuity equation. And the second line of attack that we're going to handle, that we're going to take to deal with these problems, is what's called the Bernoulli equation. So I'm just going to give you the Bernoulli equation, then we're going to talk about it, and hopefully we're going to recognize it as an old friend. Really, the Bernoulli equation says this: P1, where P is pressure, is equal to, sorry, was not ready for the equal sign yet. Here we are. P1 plus 1/2 rho V1 squared. Now this is a speed, not a volume. We're going to have to start taking my little notational convention into account. If you see a V with a little tail on the top, that will be a capital V, a volume. This is a lowercase v, it's a speed. Call it a velocity if you want to. Plus 1/2 rho V squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. If you're in my class, your book actually just gives it to you in this form. P plus 1/2 rho V squared plus rho GH is equal to a constant. What they're doing is, this is the same thing. They're not subscripting, and they're saying that whatever the sum of all these quantities are has to be a constant. That's actually what I'm saying here. This form is usually more useful for solving problems. So what in the world is this equation? What in the world does it mean? And how can we get some information out of it? So to begin with, in this video, we're just going to talk about what this means. And in the next video, we're going to start seeing what we can get out of it and how we can use it to solve problems. First thing I would say is, let's remember, we defined pressure as a force per unit area. But then, by examination of the units and looking at different things, especially the change of pressure in a fluid with depth, I said we can think about this as energy per unit volume. That is to say, energy density. All right, a mass density is a mass per unit volume. Energy density would be energy per unit volume. That's how we typically think about pressure. Of course, it's also a force per unit area. That's how it's defined. But in something like this, let's see what we can come up with this. When I say 1/2 rho V1 squared, well, 1/2 anything V squared should immediately call to your mind kinetic energy. There should be a little kinetic energy icon jumping up and down in your mind, waving a red flag, saying, hey, look at me, look at me. Anytime I see something GH, what do I think of immediately? Gravitational potential energy. And then when I remember that buried inside that rho, that fluid density, is a mass per unit volume, right? What do I get out of this? I get 1/2 mv squared over the volume. I get the kinetic energy per unit volume. For this, I'm going to get the gravitational energy, potential energy per unit volume. So what we're saying here is that the pressure in a fluid, the internal fluid pressure plus the kinetic energy per unit volume plus the gravitational energy per unit volume has to equal a constant. Right? That means the sum total of all this stuff can't change. I certainly hope that that sounds a lot like conservation of energy to you. This is just another expression of the conservation of energy. You can think of the continuity equation as a conservation of mass. That's not something we deal with in this course a whole lot. It turns out mass is conserved unless you're dealing with nuclear reactions, and then it gets changed into energy. But there are definitely no nuclear reactions here, so you can think about this as a conservation of mass. But most importantly, Bernoulli's equation is just another expression of the conservation of energy. This is how we think about it, and this is kind of what this means. In the subsequent videos, we're going to investigate some special cases of this. What happens when my height doesn't change, right? What happens when this rho GH over here is the same as this rho GH over there? What can I learn about that? And then we'll look at systems where the speed doesn't change, and we'll see what this means and how we can approach it. Before we go there, let me just remind you that if I'm looking for a change in speed, right, the continuity equation is probably going to be the best way that I can get there. So very often we use these two in tandem to solve problems. If we need to know how the speed changes, the continuity equation is our best guess on how to do that. Not guess, it's our best tool for how to do that. And we like it because it basically depends on physical parameters of my container, the area, and how that changes.